The Casey building is a 4-storey infill, if you like, into what is currently a courtyard. What we were really interested there early days in the design was how could light get through the new 4-storey building into the level 4 or the Bowen Street level areas of the building. And that started then to lead to this idea of potentially using angles as this design driver to optimise sun ingress into the area. It's a key space in the building. We really wanted to highlight that key space by giving it great access to natural light.
Best design happens when everybody is designing together. It gets called holistic design in the marketplace. Arup is very strong on that front. We call it total design, and it was a part of original Arup's philosophy in engineering. Casey building was interesting in that they wanted these sloping columns and sloping light shafts coming through the building. And so we talk about, right, how do you do that structurally? There's obviously, if you have a leaning column that wants to fall over, you need a stability system to hold it all up. So you talk about whether that's braced shear walls or whether that's portal frames. And in Casey, it was both. It was portal frames in one direction and braced frames in the other direction. And that's what concept and scheme design is all about. It's coming up with those big ticket decisions that decide, what the building is going to look like and how the building is going to stand up, how it's serviced and where the ducts are running and how it's all nesting in with the structural steelwork and which bits are exposed, or, where the ceilings are, all of that sort of thing. So that's the job of concept and scheme design. Then you get into design development, and that's really actually just putting that extra level of detail around that coordination. And then we'd move into the really grunt part of the design, which is the contract documentation. So you have a lot of people jump onto the project and actually do all of the detailed numbers and drawings and everything else. And that's where the real sort of burn of time and money spent designing comes. This is an unusual project in that contract documentation was taken to 80%. And then at 80% we stopped. It got put out to tender, and Lend-Lease looked at our drawings and put a price on the steelwork and the work that we'd done to that date. That was actually quite difficult as well, because we're stopping at 80%. A lot of the detail hasn't been sorted out, and the detail can affect the macro as well. So the connections can actually change the member sizes once you start to sort them out. All added to the fact that this is a building that's in and around existing buildings that have been there for a long time. We took the existing drawings and we did a whole lot of supplementary investigations as well. So we did a little bit of opened up a few joints here and there and that sort of thing. Tried not to be too disturbing of the operations of the campus, but we did enough to actually give ourselves confidence that the things we were finding were matching up with the drawings that we had. We were touching the existing building in almost 200 plus places, and out of that, it's a very small percentage of our surprises that came through. Once we finish our design, we can take that model and then give it to the shop drawers, who will actually use it as the basis of their fabrication model. So they'll then use that to form the actual individual piece drawings that you get to fabricate each piece of steelwork. So that original geometry gets transferred all the way through to the final guy doing the welding and cutting the steel on the fabrication floor.
So what happens at a steel fabrication factory is steel sections arrive from steel merchants and other loose fitments, and then they're assembled into the final members that are required for the structural steel erection on site. There'll be some laser and plasma cutters that'll cut up the loose plates that are required. There'll also be various welding techniques that are employed in the factory as well. There's many different types of steel, and I guess that's what we call different section types. So that'll be called up by the engineer on the structural drawings, whether it's universal beams, box sections, angles and the like. Then after the sections have been fabricated, they then get transported to a paint factory where they're prepared. After they're finished at the paint factory, that's when they get loaded onto a truck, and then they're basically transported out to site for us to install them.
The steel, once it's manufactured via the shop drawings, will always have a identification number or a beam number placed on it. When the structure is required to be installed, will call up for those particular members off the shop drawings, and the beams that are required for that installation will be delivered to site. When the beams get to site, we look at the sequence in which we need to install the steel in, and that determines which beam goes up first, second, third. Some of these beams need temporary support whilst we're constructing, and that's done by temporary engineers for the structure to ensure that the stability of the structure is there at all times.
Key factors that need to be considered when you're installing structural steel is the site environment, what restrictions are placed on you in terms of installing the steel. Also, the size of the elements you can deliver to site, which is typically governed by the transport and what can be delivered. And then also, thirdly, is the capacity of your craneage or materials placement on site. So the capacity of that will determine the weight and thereby the size of the sections you can deliver. So the bolt selection will be determined by the engineer, and he'll specify bolts based on the capacity, the tensile capacity and the size. And that's determined through his structural design and load run downs, and each connection will have a specific bolt design that will deal with the forces that are going through that connection.
During the installation process, there's various checks that's done by the structural engineer. The structure installer also does ITPs, which ensures that bolts are fitted correctly, the right size, the right type, and to the right tension.
There's a lot of laws that govern structural design, and those laws have changed over time. And a big change that's happened along the way is a requirement for a building to stand up under earthquake load. So that's in the current code, but it wasn't in the code back in 1970s. We had to be really sort of clever about how the new building or the new part of the building would either connect or not to the old building. So in the case of the Casey building, it doesn't actually connect structurally to the old building. So the Casey building is an oil rig structure, if you like. So it has its 4-story structure above ground, and then it has big columns that go down through the 2-story basement below, and it doesn't touch the existing structure that it passes through. So they can all move separately, and particularly in an earthquake environment. That means that any join between the new and old structure where you might walk across the floor where they're joined, you need to design movement joints that will take up the movement. So the plates that cover the hole do move appropriately so that the buildings can do their own thing.
So a lot of buildings out there are designed for 1 in 500-year events, say, for winds or earthquakes. And 1 in 500-year events come along 1 in 500 years, so they don't often get tested. Whereas when you're designing for a lateral force due to dead load, it's there. So you need to put a lot of thought into how the building moves sideways, because the building moves sideways. It's got facades, it's got all of the architectural finishes, it's got mechanical surfaces, lots of different things attached to it, and if the building's moving too fast sideways, it's going to pull all of those things apart. So you need to actually limit those movements to protect all of those elements. So we put a lot of thought and effort into those designs, and a lot of effort was put into mapping out what the actual movements were, so we could pass all of that on to the other people designing glass facades or plasterboard ceilings or whatever it is that came along after the structure. Critical factors to actually make sure steelwork design is a success, I would say, are to start with the erection method, so understand what the site constraints are in terms of lifting and access, how you're going to need to break up that steelwork, get it to site and erect it. Equally important is all of the detailing. It's very important to get the joint detailing right, because quite often they're the most highly stressed part of the structure. The other big thing in steelwork is understanding the deflections and movements. Understanding how the structure is behaving and moving will help you through to the end of a good steel structure.
Key success factors which relates to structural steel fabrication installation is all about having really accurate shop drawings. If the shop drawings are right and they're fabricated and the elements are fabricated to the shop drawings, site installation works really well. It's all in the preparation, and if it's been prepared well and designed well, it goes up very easily.